In this video, we're looking at a vector function that traces out some path in two-dimensional space, and we want to find the velocity and acceleration vectors for the way that this motion is happening. So the first thing that we want to do is sketch the curve, and in order to do that, we're going to remove the parameter because we may or may not be familiar with what this looks like in two-dimensional space. I'm not familiar with it, so I need to remove the parameter, write it as a rectangular equation in order to sketch the curve. So we have the parametric equations that x is equal to t squared minus 4 and y is equal to t. This is going to be a simple conversion because we already have that y is equal to t. We can just make a direct substitution into the x parametric equation and get that x is equal to y squared minus 4, which is a parabola. Let's see if we can get this into a standard form of the equation of the parabola, which would be y squared is equal to x plus 4. And now we can see that the vertex of the parabola is going to be at the ordered pair negative 4, 0. And the fact that the a value is a positive value here, this is going to be a parabola that's opening off to the right. So let's use that information to sketch our curve. We have negative 4, 0 as our vertex point. If we wanted to find our y-intercepts, we could plug in x is equal to 0, and we would get that y squared is equal to 4, or y is equal to plus or minus 2. So when x is equal to 0, I've got the two y values, positive 2 and negative 2. And this is enough for me to get a basic graph of my parabolic path. And we could do a little better with our graph here to get the orientation, and we could do that by simply plugging in a couple of values for the parameter. And if t is equal to 0, we end up with the vector output negative 4, 0. And if t is equal to, let's say, 2, we get the vector output that is 0, 2. So that's enough for me to say that at time is equal to 0, I get a vector whose terminal point is at negative 4, 0. At time is equal to 2, I get a vector whose terminal point is at 2, 0, and therefore my particle must be traveling this direction around the outside of the curve. Now, part B of this question is asking us to find the velocity vector. The velocity vector function is simply going to be the first derivative of the position vector. And in order to calculate the first derivative of this position vector, we calculate the derivative of each of the individual components. So that's just going to be 2t and then positive 1. So this is my first derivative vector function. And then the acceleration function is going to be the first derivative of the velocity vector function, or the second derivative of the original position vector. Let's look at it from the perspective of the first derivative of velocity, and when we differentiate the velocity function, we have the derivative of 2t, which is just going to be 2, and the derivative of the constant 1 is going to be 0. So what this then tells us is that the acceleration vector is a constant vector having the same direction and the same magnitude throughout the movement of the particle. Now, let's consider part D, where we are asked to find the velocity vector at time is equal to 2 and the acceleration vector at time is equal to 2. Well, we know that the acceleration vector is going to be the constant vector 2, 0, because it doesn't matter what we plug into the parameter when the acceleration vector is a constant. The velocity vector, however, turned out to be 2t as the x component and 1 as the y component, so we'll plug that value 2 into the parameter, so it's 2 times t, and then 1 is the output, so I'm going to have 4, 1 as the velocity vector at time is equal to 2. So let's look at our velocity vector and graph it as if it were originating at the position of the particle. The velocity vector is describing the direction and the magnitude of the movement of the particle at that time. If we have the initial point of our velocity vector at the position of the particle, then we're going to move 4 units in the direction of x and 1 unit in the direction of y. to get the terminal point of my velocity vector. Now I can already tell that my drawing is not to scale because I actually look like I'm going 2 units in the direction of y, but that's because my parabola is just a little bit too wide. So our velocity vector is going to be v at 2 here. It's pointing in the direction of motion, and the magnitude of the velocity vector is representing the speed. So the longer the velocity vector, the faster we're traveling. The shorter velocity vector is a slower speed. Now, let's also look at the acceleration vector. Acceleration vector is a constant vector to 0. And so we'll go ahead and plot that, again, having an initial point that's at the position of the particle at that time. We're going to go 2 units in the direction of x and 0 units in the direction of y, and we see that our acceleration vector at time is equal to 2 is moving in this direction. Now this means that we're always getting a push on this particle, pushing it to the right. And since this acceleration vector is pushing in the same direction as the direction that the particle is moving, we can anticipate that the particle is going to be speeding up as the value of time is getting bigger and bigger and bigger here. So let's take a look at the next part of this question, which is to find the value of r evaluated at 3, which is the position at time is equal to 3, the velocity at time is equal to 3, and we already know that the acceleration at time is equal to 3 is going to continue to be 2, 0 because the acceleration vector was a constant vector. Let's figure out where we're located at time is equal to 3. So here we have our position and our velocity vectors. As a reminder, we'll plug 3 into the position vector and we'll get the output that is 3 squared is 9 minus 4 is 5, and then 3 is the y component of that position vector. When we plug 3 into the velocity vector, we're going to get 6, 1, and then of course again the acceleration is still that constant 2, 0. So let's plot all 3 of these vectors back into our original sketch. So I'm going to erase everything except for that velocity vector because I want to bring your attention to the fact that when we plug in 3 to the position vector, let's initiate it at the origin so that the terminal point is going to be a position on the curve. We found our terminal point to be 5, 3. So the vector function evaluated at 3 is a vector that terminates at the ordered pair. Ordered pairs has soft brackets, a vector has pointy brackets. 3 into the velocity vector gave us the vector 6, 1. Let's graph that initiating at the position of the particle at that time, and we're going to move 6 in the direction of x and 1 in the direction of y. I'm almost off the screen, but what we can be able to tell here is that this velocity vector is longer than the first one. It doesn't really look like it here because I've run out of screen space, but it should be a longer vector. And I know that because the acceleration vector is pushing that particle in the same direction that it's traveling. If we get a push in the same direction that we're traveling, then the particle is going to be speeding up. We know that it's in the same direction that we're traveling because, let me zoom in here just a little bit, because the angle in between these two vectors is less than 90 degrees. If the angle in between the two vectors is less than 90 degrees, then my particle must be speeding up because the acceleration is pushing it in the same direction that it's traveling. So let's summarize that. When the acceleration and the velocity are moving in the same direction, and we'll say, in other words, when the angle in between these two vectors is strictly less than 90 degrees, then we conclude that the object is speeding up. When the velocity vector and the acceleration vector are not in the same direction, or we could say in opposite directions, so what that might look like is having a velocity vector coming out this direction, pointing in the direction of the motion, and the acceleration vector might be pointing in an opposite direction, meaning that the angle in between these two vectors is greater than 90 degrees, but of course it has to be less than 180. So we'll say greater than 90 degrees, less than 180 degrees, and actually we can say less than or equal to 180 degrees. We should still say over in this direction, greater than or equal to 0 degrees, strictly less than 90. Now we've got strictly less than the 90 degrees here on both of these inequalities because when the vectors are perpendicular to each other, or when the angle in between is 90 degrees, then we have something else that is occurring. But let's stick with this second bullet point for the moment. When the object is being pushed in a direction opposite that it's moving, then that tells me that the object is going to be slowing down. But when the velocity vector pointing in the direction of motion is perpendicular to the acceleration vector, when these two vectors are perpendicular to each other, then there is no change in the speed. Acceleration can be considered a push, and if it's not pushing it forward or it's not pushing it backward, there's no change to the speed of the object.